1/3 of a famous paper on bars. This was my card, let's say. So I had to change the plan a little because most people was sick. So this was actually in the initial formulation. Of course, I should speak on tomorrow. And for the whole day. So we are splitting it also because on Wednesday we have to cover other people who cannot be here. So I mean, probably we are not exactly following the initial layout of the course, but I have split my lecture in two parts. One that is the one of today is essentially some introduction to what linear stability analysis is, an introduction on bed forms and on some topics that will be helpful on tomorrow. The idea is tomorrow to do something much more on the board, so we will forget about, at least for some part of the, well, we can do both, let's say. So we will derive the equation and do some stuff that is needed to work on the topic of linear stability analysis. The idea of the whole course, as I catch it from Guido, is to introduce you to linear stability analysis and to, let's say, as an icebreaker, okay? In the sense that, I mean, you quite often, or let's say people quite often look at these kind of things like magic. So you do things, you linearize, you make some solution, eigenvalue problem, eigenvectors, this kind of difficult mathematical things. And you end up with some physics, and so people tend not to believe it. So one of the messages that we are trying to let go from this is, okay, it's nothing different from solving the equation which describe the physics of rivers, let's say, and sediment transport and flow. It's nothing different to solve them numerically. Okay, so you're solving exactly the same set of equation. We just do some approximation that consists in the fact that, okay, you assume that the change with respect to some base data are very small, and this allows you to use some useful mathematical techniques, which are not magic. It's just quite simple, which allows you to use them and to end up with very fast information on some, let's say, characteristic values of the flow and the sediment. Okay, is not different in any way from that. There is no magic in doing this, no strange mathematical techniques. It's just taking the physics and assuming that you are just slightly changing the flow with respect to some uniform state. That is something the hydrologicians are very familiar with. So let's start from an introduction to this word. So today we will just make a walk through the word of linear stability of bed forms. This is me. This is my team in the soccer Italian championship. This is the symbol of my university. So that's much more important than one of the football, the soccer team. This is my place. It's the Department of Civil Engineering, Chemical and Environmental Engineering in Genoa. There is a very strong link between my department and the department here in Trento, because Marco Tubino, who has been the head of this department and was the first to bring here, comes from Genoa. Actually was my fellow in the graduation, so we did our thesis together. So it's a long friendship, and also many people like Guido and Nunzio Siviglia came from Genoa too, so there is a strong link between the two cities, let's say. I'm actually in a sabbatical year. The whole idea of which is to write a book on stability analysis in rivers. It's a project that started many years ago, which is really time-consuming, chronophago, as we should say in Italian. It is really time-consuming, and it took me about 2 years just to be in the middle of nowhere like I am at this moment. So I decided to take this sabbatical, to devote all my time to the writing of this book, which essentially is a synthesis, or it's a way to look at all the work I and other people have done on the linear stability of platforms in rivers in the same framework. It's something that is you cannot appreciate when you're looking at a single paper. So the idea is to have more time and more space to do so. Actually, I'm doing everything but writing the book, but there will be time for this also. Okay, that's for me. So this is an example of instability. So we'll start with the same way, the same route that Guido followed in the last few hours. So I'm trying to give you some very simple concepts in instability. This is a Van Gogh, of course, and what you see in the sky is something that's very similar to a kind of instability, which is called the Kelvin-Helmholtz instability. You can see an example of Kelvin-Helmholtz instability in the clouds in the photo there. And it's a kind of instability that starts when you have a shear. So we have two layers, like sketched in the sketch on the left. You have two layers with different velocity. At the interface of the two, you have a shear, and this shear can be unstable, leading up to those kind of pattern. Okay, instability and pattern are two things that are strongly connected, one to the other. One of the father of morphodynamics, which is the science that studied the interaction between a flow and the container, was Kennedy. Was in the 80s, was the one that introduced this idea that bed forms, so the pattern that you observe in rivers, are the result of an instability process. Okay? So from that paper on, there have been an amazing amount of people, especially in the 80s, who applied this kind of techniques to the world of morphodynamics. That this, way to study patterns was far better known in fluid mechanics. And for example, Kelvin-Helmholtz instability has been studied from many years ago, but in the 80s we started to apply, people started to apply this technique to the field of morphodynamics. So when you start with trying to make people understand what instability is, Kelvin-Helmholtz instability is a good example. So this is a lab. So the first one is in the field. in the sky, in the real sky. The second one is the same kind of experiment, so the shear layer the instability of a shear layer in a lab. And you can see that you see this formation of this pattern that then destroy at some moment. This is once again the same problem, this time with a numerical solution. So a numerical solution of equations. So in this slide you can see that you can observe some phenomena in the field. You can reproduce them in the lab, so you understand what is the thing that is causing this pattern. And then you can reproduce them with a numerical model, for example, solving some equations. Okay, so the idea is that if you build the right model, you can see the same phenomena that is shown in the field and in the lab. What means the right model? This is actually a very difficult question to answer, because we will see example of a shallow water model, but indeed you are very free to define a model which can be as complex as you want. As the complexity increases, it also increases the complexity of the solution, so of the problem. So the only real answer to how I should complicate my model of this problem is as much complicate as you need. So every of these patterns, every of this instability depend on some key feature of your model. So you have to build the simplest possible model which has inside of it the mechanism that drives the instability you're looking at. So there are some models that are too simple for some instability, and I will show an example of this tomorrow probably. So are too simple for showing some kind of instability, but complex enough for showing another kind of instability. There are some patterns that you observe in the lab and in the nature that are indeed the result of an instability, but for being able to describe in a linear stability or in a numerical solution that kind of instability, you need a very refined model. There are patterns related to secondary flow in rivers. So the flow that let's say the kind of current that develop in a section of the river that require a very refined model of turbulence. If you don't use a refined model for turbulence, which means a nonlinear closure for the Reynolds shear stresses, for those of you who knows a little more about fluid mechanics, if you are not introducing in the model that specific refined model of turbulence, you will not be able to see anything. Okay? So it really depends. It's a kind of a trial and error also when you formulate the stability analysis, because you need it to be complex enough for the with your model for the pattern that you want to reproduce. Okay, and so I mean you can try with the simplest and then make it more and more complicated, or you should already know how complex your model should be. Okay, so what is the real concept of the stability analysis? Probably Guido has already told you something like this. The whole idea of linear stability analysis in general, and in particular for bad forms, is that you think of the phenomenon as the superposition of two states. You know that when you linearize equation, usually when you have linear equation available, let's not talk about linearization, but when you have linear equation, then you can superimpose different solutions, which means I have solution A, which is solution of some linear equation. I have solution B, which is another solution of the same equation. Then every linear combination of these two solutions is automatically a solution of the complete problem. Okay? So if you have solution A and solution B of some problem, then a constant times the solution A plus another constant for the solution times the solution B is again a solution of the whole problem. Okay, so the whole idea in this is in general a way to study stability, so to assume that you have a superposition of states, and in particular you have, for linear stability analysis, you have a base state and a perturbation, which means a periodic variation in space and time of the same function, of the same quantity, which can be the velocity, the flow depth, the free surface of a flow, but also the I don't know, the sediment discharge, for example. It's always thought in linear stability analysis at the superposition of these two states. These perturbations are related one to the other. This is another important thing. So you have a feedback. When you modify your initial system, your base state, for example, assuming that the bed in a river is not flat but has a bed form on it, this perturbation of the bed, of the shape of the bed, induces a change in the flow. So induces a perturbation of the flows, which in turn modify the perturbation you have done of the bed. So this is the essence of the process. There is a feedback between one perturbation and the others, so that you think of perturbing slightly, for example, the shear layer that you have seen in Kelvin-Helmholtz instability. So you have a very sharp change in velocity at the interface. If you assume that you have a little perturbation of that one, then this perturbation will induce an oscillation of the interface between the two layers. And once you have this perturbation of the interface, then this will change the flow also. And so you have a possible mechanism, a possible feedback mechanism, so that once you study the time evolution of the system, of this perturbation, you can decide if the system is stable or unstable. So given some perturbation, if the system, if the reaction, let's say, of the system to this perturbation is such to increase the perturbation, then the system is called unstable. Okay? Otherwise, if your system, subject to a change, to a perturbation, tends to reduce that perturbation in time, then, and so the perturbation will decay, then the system is said to be unstable, to be stable. Okay, so the whole idea is that you take this this base state, whatever it is, you give a little kick to it, a little modification of this state, and see what happens. if the kick you have done just creates some oscillation and then this oscillation disappears, then the system is stable. If after the kick the system explodes, so the perturbation amplifying time, then is said to be unstable. So what is linear stability analysis all about? It's about studying the stability of a system by perturbing the variables that describe the state of the system. Okay, this is very abstract. The concept is abstract, so it's not clear probably to most of you what is the state of the system. But let's think of a system of something characterized by some values of the parameters. The fruit number for a flow, I don't know, some flow rate and whatever, some flow depth. So a state which characterizes some set of parameters that characterize this system. The whole idea is that you just perturb these parameters, these variables, and see what happens. If the system moves away from this state, from this initial state, then it is unstable. So studying the stability, perturbing the variables means perturbing the equation, the dynamical equation that describes the state of the system. So you have some equation which describe, for example, in our case, the flow and the sediment transport, and the relation between the two. Perturbing this equation means exactly to studying the dynamics, how the system evolves in time, okay, which is called the dynamics. So you perturb not only the variables, but also the equation that describe the state of the system. Okay, the system is in some point in some space of the parameters, and try to transform some very abstract concept in something which makes sense to you. It is not easy. So you assume that you have some point in a space which describes the state of your system, then you move it slightly and see if that one stays there or move away and goes in another point. What is typical of linear stability analysis? Linear, I'm not sure I have said it before, but the moment in which stability analysis becomes linear is when you assume that your perturbations are small. Okay? So the whole concept of linear stability analysis is to study the system when you give just a very small perturbation of the state and see what is the tendency of that system. So if there's something that I just slightly perturb it and then it moves away, then it's unstable. If I just slightly perturb it and then it goes back to the place, to the steady state, then it's stable. So the characteristic of linear stability is that the perturbation, because of the way you solve the system, evolve exponentially in time. Okay, so it means that they grow exponentially if the system is unstable, or decay exponentially if the system is stable. Of course, this is unphysical. Okay, so the system do not explode. Actually, it's just the linear analysis that is valid only when this perturbation are small. Okay, so as soon as they increase exponentially, at some moment, non-linear effects, which are the one that you ignore in linear stability analysis, becomes important and leads you to a steady state, which is the one that you observe in the lab and in the field. Okay, what you observe are patterns which have a finite amplitude. Okay. With linear stability analysis, you don't have any information at all on the amplitude, so on what happened in time. You just know if the system is unstable or stable with those specific value of the parameter that you are feeding your analysis. Okay, which is not a big deal of information, but is important to know. For example, you will know by linear stability analysis if in some region in the parameter space you should expect to see one kind of value form or another. This is a very important information because it allows you to create what is called a regime diagram. Okay, a diagram which describes the characteristic parameters of some problem and tells you, okay, in this part of the space of the parameter, you should observe dunes, here anti-dunes, here alternate bars, here ripples, and so on. Okay, and this kind of regime diagrams are very important in the practice, and linear stability is the only way to have an information of that based on theory. Okay, on the solution of the equation. The only other way to have information is to do experiments, okay, which are a very important part of the task. So the first thing, if you want to know what happened in some space, and you just do experiment there. But then to see the boundary between one region and the other, you need to prepare a lot of experiment. And linear stability analysis can be helpful for defining theoretically those regions of existence of one bed form with respect to another, for example. Back to the characteristic of the, so we have no information on the amplitude, we have information on the growth rate. We will discover that if the growth rate is positive, the system is amplified, is unstable, tends to amplify. If the growth rate is negative, it will decay. But we also have information on the celerity, on the wave speed of the bedforms, which is again an important information that you obtain from linear stability analysis. So you know the characteristic speed, okay, of this linear bedforms, and you specifically know if they are moving downstream, so if they propagate from da monte a valle, come si dice? From upstream to downstream. Very good. If they propagate from upstream to downstream, so if they have a positive wave speed, or upstream, so they have a negative wave speed or celerity. Please stop me, okay? I should have said this at the very beginning. So the whole idea of this is just to interact with you. And you are coming from very different say cultures. So, I mean, this course has no sense if you think this is magic. Okay, so every time you have this bad feeling that there is something that you don't understand, or it means that I have not explained it, taught you well enough. Okay, so it's the problem is in the one who speaks, not in the one who listens. But if you have doubts, just every kind of, just stop me and ask. Okay. That's it. This is the second question, which is why doing the linear stability? I already have explained and give an answer to some of the question, to this question. Why doing the linear stability analysis? I've tried to put here some points that can deserve a thought. Well, the first thing is fast. It's extremely fast. When you have you did all the calculation, and sometimes it's a matter of one afternoon, you can explore the field of the parameters in a very fast way. You have partial information because they are related to linear, to small perturbation of your system. So it's not exactly what you observe, but you have a very, let's say, rapid information on the region of instability. So if the system in that region, in this parameter space, is stable or unstable, and on some of the characteristic of the weight. Okay, it's very fast. It's much faster than doing numerical. It's much faster than doing experiments. So it's something that should be used to to drive the other way of investigating a physical phenomenon. Okay, this was what I just said. So because it's fast, then it allows you to investigate a wide range of flow and sediment parameters. Okay. One of the problems in the papers that you see in the literature now about numerical simulation, for example, of the river or with active sediment transport, they are extremely complicated, extremely requiring in terms of CPU time. So you build up a very complicated tool, and you are usually able, after a couple of months, to describe one single status solution of the problem. Okay. So for building up a regime diagram, so something which covers a space, it's almost impossible in terms of numerical simulation, and also in terms of experiment, it's very hard to be done. This is another important point. The system of equation that you are using for building up your linear stability analysis are exactly the same equation that people doing more complex numerical model are using. Okay, so you are using the same set of equations. You're just assuming that perturbations are small. So you look for a simplified solution which is valid when the perturbations are small. But you are solving exactly the same, so there is no magic in it. If there is a magic, so those patterns that you observe are already inside the equation that you use to model the flow and the sediment. This is the important thing. Okay? Because those kind of periodic solutions that build up the pattern, think of Kelvin-Helmholtz instability, are contained in the physics and in the equation that describe the physics. Okay, this is just a way to finding out very fast some simple information which is already contained in the equations. Another important information that comes out from, I told you that you have no information on the amplitude of the from a linear stability analysis, but you have information on the growth rate, and specifically on the growth rate that you have for any wave number of the solution, or wavelength, let's say. So you have periodic disturbances, and think of a complete range of this perturbation with different wavelength. For each of them, you will know if that one is stable or unstable. And so you can build up for some values of the flow and the sediment parameter, you can build up a growth rate for each wavelength or for each wave number. and discover which one is the most unstable, so which one has the largest growth rate. Okay? The whole idea is that the perturbation with the longest wavelength, the largest wavelength, will, which is the most unstable from the linear point of view, will in some sense mark the evolution of the system. So the system will choose that particular wavelength and just increase the amplitude using nonlinear effect just to reach an equilibrium amplitude. Okay, but the whole idea is that the linear, the wavelength which is selected by the linear analysis is the one that you observe at the end. Okay, of the when they, so there will be much more changes to amplitude due to nonlinear effect than to wavelength. There will be changes in that, but once you are able to know the wavelength of the most unstable, so the one that will be selected among the variety of perturbation that are fed to the system. When you know the one which will be selected, then you have information on, for example, how big a computational box for doing a numerical solution should be. Because one of the problems of numerical solution is that you start from some base state as here, then you give perturbation and you see how they evolve. But until the end, you don't know how long are the disturbances that amplify or decay in time, and so you don't know how big the box, the computational box, should be in the direction of the particles. So you want the computational box in which you solve the equation big enough to contain at least 2 or 3 wavelengths of your pattern, of your perturbation. And since you cannot adjust the box when you are doing a simulation, you start from some box and see what happened inside, then having information on how long should be the background that you should observe, it's really valuable for people doing numerical. Then, this is a subproduct of the linear stability. I told you that when you give a perturbation, for example, of the bed, then this creates a perturbation of the flow, which is flowing over it, which means that the perturbation of each of the variables are connected one to the other. So typically what you do when you do numerical solution is that you start from a solution from the base state, as in linear stability analysis, but then you have to feed, at least at the beginning, the system with some perturbation, it's just a seed, okay, just to see what happened of that perturbation. And when doing it, then you usually give a very small one, because you don't want to give too big changes, because otherwise your numerical code will start to have difficulties to handle these large changes. So you give a linear solution, but you have to introduce an initial solution which is just a perturbed state in which all the variables are related to the other in the right way. So if you give a perturbation of the bed, then the flow should adjust accordingly to the equation. Otherwise, you introduce noise in the simulation, okay? Because you are forcing a solution which is not natural, which is not a solution of the problem. So once again, this is a subproduct, but can be useful. So you are doing a numerical solution, you need to give a perturbed initial solution with more disturbances, and the linear analysis gives you exactly that. Oh, this is another subproduct which is interesting. As I told you, you have, suppose you have this solution, okay, with this wavelength. This is the typical output at some time of the linear solution. You can have one of these for any kind of periodic perturbation of the bottom. This is much longer than this, okay, but you have both. Okay, should be much more periodic than I'm able to draw on the board, but I mean, assume this is a sine or a cosine or whatever, which is very periodic. It doesn't change wavelength. Okay, but as I told you, you have information on this solution and on this solution, just putting in a different value of the wavelength. So you can, and the only condition is that the amplitude of this perturbation should be small. Okay, both this and both this, and so you can think of. This is not easy if you don't have any information on transformation, but you can think. Assume this one is a signal. Okay, periodic signal, like this. Okay, this is periodic. It's not sinusoidal, but it's some signal. Okay. Okay, you can think of decomposing this one in many harmonics. It's said so in many sinusoidal and cosinusoidal, longer and shorter. Okay, as the sum, as a linear combination of shorter and longer harmonics. So every periodic signal can be analyzed as they do in electronics, okay, and decomposed in a summation of sines and cosines of different wavelength and amplitude. Okay. So the idea is that you can take this solution and this solution, which have different forcings, so have different band wavelength, and make a linear combination of that, because as usual, a linear solution in a linear framework you can superimpose different solutions. So combine this and this solution plus this solution, and obtain the solution in a more complicated domain. Okay, for example, you can make the Fourier analysis, is called the decomposition process, which gives you the harmonics which build up this signal. I know this sounds awful, but try to follow me. And I don't want you to be able to do this. I just want you to catch the idea, okay? So you have this one, you decompose it in a sum of sine and cosine, shorter and longer. Then for each of these, you build up your linear solution, and then you recombine the result using the same combination, the same amplitude, and same, and with this you have the linear solution over a complex, in a domain which is not simply a sine or a cosine, but has a more complicated shape. Okay. That's it. Don't go farther with this. Okay. Okay, the last part of this is essentially on bad form classification and scaling. So it will be, for the most part, a journey to the kind of bed fonts you can encounter in rivers. And then we will do some reasoning also on the scales, so the characteristic length and the characteristic parameter of the flow in rivers. This is the pi channel, Guido, is correct?
Yes.
The pi channel in the laboratory, which is called pi because it's
Because it's 3.14 meters wide.
wide, okay.
Like pi.
Strange people here in Trento.
Walter designed.
Walter design, okay.
But it's wide.
It's wide. This is because bed form classification has been mostly done during experiments. Okay, field observation and then experiments to be able to construct those regime diagrams that we will see at the end. And this is a very famous paper. Actually, it's a report because it's a thick one, which was done in the 50s, in 5 years, by these three guys, Guy, Simons, and Richardson, that are probably not so known in the literature, but they are very much quoted in every experiment because they were able to build up a database in these 5 years, a database of 340 runs. Okay? Each one of them was characterized by a bed form. So they set up, they move in the space of the parameters. This is probably the most, I think, in the experimental paper now on alternate bars or dunes, usually you have a maximum of 10 runs, okay? And it's quite difficult to investigate the space of the parameter, which means changing slightly all the parameters to examine the state of the solution. And they did an amazing job, and still is a kind of a reference in the field, because there are so many experiments on dunes, anti-dunes, ripples, plain bed, upper plain bed, and things like that. This, for example, was the 60s. They don't have much. They do not have detailed measurement. But they were able to say, okay, this is run 16 with this flow. This was the flow depth. This was the. We observed dunes. We observed ripples. We observed whatever. This was the sediment. This was the average flow depth, and everything that is needed to build up a regime diagram. Dunes and ripples, we will go on this a little later, are two kinds of longitudinal bed forms. Okay, so bed forms that are periodic in the longitudinal direction, quite similar one to the other, controlled by different parameters. So this is an example of what I was saying at the beginning. Depending on how you build up your model, then you will be able to see dunes or ripple or both. Okay, so you should build up a model simple enough, but able to catch what is the important mechanism which leads to the formation of a ripple instead of the dunes, because you will not be able to see the difference in a linear stability analysis. They look exactly the same. When you think of a longitudinal perturbation of the quantity, the solution is exactly the same for one or for the other. It's just the wavelength that is changing. Typically ripples are much shorter, as you can see, than dunes. Okay. This is also to give you an idea on how complex is the real thing. Okay, so I will try to describe the dunes and bedforms in general as sines and cosines function, but they are something much more complex. Still, the information that you get when you assume that they are sinusoidal, the information on the wavelength is pretty good. Okay, so you are able to transfer that information on the real thing. Even if when you're looking at this, it's quite difficult to recognize. So if you know what you are looking at, then you can find dunes or you can define ripples. An amazing thing is that there is a lot of confusion in the literature between dunes and ripples for the reason I was telling you. But the experimenter was pretty able to label them. Just looking at the experiment, they were saying, okay, this one are ripples, these one are dunes. They have no doubts on this. So people that is trying to interpret the result, on the contrary, have difficulties because they are just, you have no a discriminant between the two. So you have no instrument to tell what is a ripple and what is a dune from, if you treat them as sinusoidal disturbances. Okay, I will go back to the experiment of these three guys in soon, when you will look at the scales of these quantities. But then let's do some. Let's have a walk through the fluvial bedforms. The most important fluvial bedform that you observe in a straight river. This is again a very important simplification of the problem. Usually rivers are not straight at all. They are meandering typically, and just the fact that is meandering, they are meandering, induce a modification of the flow. So a meandering river has not the same flow than a straight river. And most of the consideration of the whole of the consideration I will do in the following are relative to straight river. Okay, so no planimetric variation, but just a straight reach of the river. Okay, you can observe dunes on the bed of this North Loop River in Nebraska. Just to mention it, this is, I will present you 10 or 15 slides which are taken from the, which I took from the Gary Parker book on morphodynamics. This is freely available. It's a very interesting and complete kind of electronic lecture. So if you have not been there, then just have a tour on this presentation. I just extract some of the presentation on bedforms. All of the one that is, you see there is copyright Gary Parker, which I report there. So I should pay probably some fee to him, but I will not. Gary Parker, if you don't know him, he's really a guru of the morphodynamic community. Okay, I was one of the first who started to study stability in particular, but it's really a guru of morphodynamics and a good friend. Okay, ripples. You can see ripples in that river there. You have to look much more carefully than for dunes. You have to much more closely to the bed, and you will observe this much shorter wavelength. Is said the wavelength lambda is about 10 to 20 centimeters. You tend to observe ripples in river when you have very low transport rates, and the bed material is fine. Okay, so you need to have these conditions. So you have to be close to the critical shear stress for motion, or the critical bed shear stress for motion. You are already familiar with sediment transport, at least in different way. So you know that you need to apply a finite stress to the bed for the sediment moving. Okay, so if the stress is too low, the sediment will stay still. If you exceed some threshold in the shear stress, which can be the shear stress or some non-dimensional form of the shear stress, they will start to move. So for observing ripples, you have to stay very close to the critical shear stress for motion, above of it, of course, otherwise you will have no motion of the sediment, but not too much. So if you increase too much the shear stress and you have a stronger current of the then dunes will start to form. And the other important thing is that the sediment size must be small, so the sediment must be sand, fine sand. You do not observe ripple formation in gravel. Okay, it's something that you observe only in sand, and typically less than 1 millimeter. Okay. So what you expect your linear stability analysis to predict is that if the shear stress is low and the sediment is fine, then you should observe the formation of ripples. Then if you have a largest value of the shear stress and possibly coarser sediment, then you will observe other bed forms. Okay, actually it's exactly what happened. So this is a reason. If you formulate one problem, this is one reason for which is an upside for doing stability. Ripple migrates always downstream and have this asymmetric shape, which is sort of triangular. They have a stoss side, which is called, this side is the stoss side of the bed form, which is actually gentle sloping, and then a front, so a much steeper front, which is called a lee. Okay, so the stoss side of the bed forms is upstream of the crest. Typically, the lee side is downstream of the crest.
Excuse me. The migration of the topology is in the same direction?
Yes, it is. So this is the flow. This is the migration of the bed form. It's migrating downstream for ripples, always. Okay, because the only way to have upstream migrating is having anti-dunes. So anti-dunes, which will we describe in a moment, are bed forms that migrate upstream, but that you observe at much higher value of the shear stress. So the lower values of the shear stress, which means low fruit number, all the bed forms are migrating downstream, both dunes and ripples. The other important characteristic of ripples is that there is almost no interaction with the free surface. So if you have the formation of ripples on the bed, then you will not observe almost any change in the free surface. Okay. Second, in complexity, kind of patterns is dunes. In a sense, they are similar to ripples. As you can see, they have the same kind of triangular shape with a gentle soft side and a steep lee side and a steep front. They also migrate downstream, but they are much longer. Okay, so the wavelength of dunes typically scale with the flow depth. Okay, so this distance here is of the order of some flow depth, average flow depth. Let's say 6, something like that. 8. Okay, typically. On the contrary, ripples are much shorter than that, much shorter than the flow depth. And another distinctive feature of the dunes is that they affect free surface. Okay, so you have a modification of the free surface when you have the formation of dune. On the contrary, ripples do not modify, are not felt by the free surface. Okay, here is a photo in which you should be able to guess at least the wavelength. There are 2 people there. So this, they are, let's say, 1 meter or something like that in plain view. Another important feature, which is important for the physics, is that the perturbation, the free surface wave, okay, is such that is in opposition of phase with the bed. Okay, so when you have the crest here, the free surface will have a trough. Okay, so if you are looking at a view, this is the bed, this is the free surface. Okay, they are in opposition of phase, almost. It's not exactly in opposition of phase. So you have a contraction on the crest and an expansion of the flow in the trough. Okay. Is this clear? What is in opposition of phase? In phase, in opposition of phase? Yeah.
Sorry.
Yeah.
Is it possible, like meandering river, the skewness of the migration also in bed form? I mean, do we have a skewness, downstream skewness based on something similar to aspect ratio? The skewness.
This shape here?
Yes.
And what about it?
The question is that do we have something similar to skewness also in bed form, downstream skewed or upstream skewed?
No, they are always on. Okay, they are almost always this shape. So downstream skewed.
Mm-hmm.
Okay. Was this a question?
Mm-hmm.
Okay. Yes, they almost invariably have this kind of skewness. Take into account the fact that we will always deal with just sinusoidal. So I mean, it's not. We will not be able to represent this shape apart from the superposition thing I told you before. But the important thing will be to be able to guess this wavelength. Okay, so the wavelength of this will be very close to the wavelength of this, even if the shape of the bed form is different. Okay. This is a movie. This is scaling. This is the same river that has been shown before. This is black and white. You have a superposition of two, actually, because this is the real thing. It's not a nice mathematical solution of it. Sometimes it's amazing. It's almost magic when you see that this very simple representation of the bed and of the variables is able to give you information on the real thing there. Here you can see dunes that are moving. Okay, so they do migrate downstream, and you also see the superposition of two different situation. It's a field of dunes here, and then there is a big bar, which is much bigger platforms. I will tell you in a moment. Okay. Now, if you increase the shear stress, what we did is actually increasing the shear stress from ripples. We were very close to the threshold for motion. Then you have dunes, which is a little higher, but still in the subcritical regime for the river. So the Froude number is less than 1. Then if you increase it a little farther, then you move to the supercritical regime, and you will have some kind of a different bed form, which is called anti-dunes, and which is characterized by the fact that it migrates typically upstream, and also the perturbation of the free surface is in phase with the perturbation of the bed. Okay? So instead of this, you will have something like this. Prima che tu te ne vada, domani mattina siamo qua, a che ora?
Siamo in un'altra aula, ma c'è in web.
Okay.
The room is on the web.
The
It's
cat
not
is on
this
the
one.
table.
I think 1P. I think it's 1P, but check.
1P?
1P like
Okay, dalle?
Palermo.
A che ora?
At 9.
At 9, okay.
Should be 1P, but check on the website, that's the right route. I left the attendance sheet to Tullio. Please sign before leaving. Put your signature and I will get it tomorrow. Every day we have to sign for all the presents. Good night. Ciao. Ciao.
A domani.
A domani.
Okay, so higher in the shear stress, then you have this kind of platforms that are similar to you. They are also much more regular, so much less skewed. They tend to be more sinusoidal than dunes and ripples. So in a sense, more similar to what you do in a linear stability analysis. They migrate upstream, so if you look at them, I don't have a movie, but you will see the platforms going the direction opposite to the flow. They are waves, so they can do that even if the velocity is downstream. Then the wave can be in each of the two directions. It's not forced to go exactly in the same direction than the flow. And again, another characteristic as opposite to dunes is that in dunes the amplitude of the free surface perturbation is much smaller than the amplitude of the bed perturbation. In anti-dunes it's the opposite, so the amplitude of the free surface is much larger, let's say, than the amplitude of the bed. Okay, this again characterizes anti-dunes. will skip this. Okay, all of the above were longitudinal bed forms, so two-dimensional in a sense, one-dimensional bed forms, so they were periodic just in one direction. And alternate bars is the simple example of a bed form which has a transverse structure. Okay, so it is a let's say they are called alternate bars because they change side periodically. So you have one bar on one side, and then the following one is on the other side, and then go on. So they are called alternate bars. They are typically migrate downstream, but they can migrate also upstream. But much more frequently they move downstream. And they have a lateral structure. So if you make a section, you will see a straight line in dunes and anti-dunes, but you will have a pool here and a crest here also. Okay, so you have a kind of a two-dimensional pattern as you move along the bed form. Okay, sometimes you have the pool on your left, and then in the second part of the bar, this is the wavelength. Okay, from crest to crest, and no, sorry, from here to here. This is a wavelength, and in a wavelength you will have for sometimes a pool on your left and the crest on your right, and the opposite in the second part of the bar. They have been, in a sense, kind of a precursor of meanders, so they are somewhat related to the tendency of the flow to become meandering, of the river to become meandering. So you typically observe alternate bars, natural alternate bars, only when the river has been straightened artificially, because sooner or later they will lead to the formation of meanders if they are free to, if the river is free to evolve. And alternate bars are just the first mode, the first transverse mode of instability. You have, instead of having just one alternate bar, so one crest on the right, then on the left, then on the right, then you can have multiple bars in a channel. So if the channel is wide enough, then you can have many bars, which are typically, the second mode is that of central bars. So you have two pools on the side, on both sides, and then a central bars in the middle. But then if you have a wider and wider channel, then you have this linguoid or multiple road bars, which are often a precursor of braiding. Okay, instead of meandering like alternate bars, because it's reasonable to assume, in a sense, that that modification of the bed will induce some modification of the banks, and then will lead to the formation of meanders. For the same reason, if you have many bars in a width of the channel, then when the flow is low, you will have the formation of many channels and what is called a braided river. Here are some photos. Here you can see some dunes in a flume, in a laboratory channel. You see dunes superimposed on what is called a point bar. Okay, when you have a meander, then you have the formation of a bar which is not an alternate bar. It's something which is related just to the fact that you have a curvature, and that curvature of the channel induces the formation of what is called a point bar, which is steady, it's not moving, it's just forced there by the by the curvature of the channel. And you can see dunes superimposed on other bars. For example, the white part there is the point bar, is the deposition area that you see on the inside of a meander. And superimposed on it, you can see a pattern, distinctly a pattern which is much shorter. Another typical thing that is characterizing alternate bars with respect to dunes is that they are much longer. Okay, so a point bar, but also an alternate bars are typically much longer than dunes and anti-dunes that are other category. These are alternate bars. You can recognize quite easily this diagonal front, which is typical of alternate bars. Okay, you have a crest here. This is the front, and you have another crest here. So you have an alternate pattern. These are alternate bars in the field. This is a famous Rhine River, in which you can see easily in this straight reach the formation of these alternate bars. Okay, this is an example of multiple rows bar. You can see that there are many bars in the channel, so it's a very wide channel. And these are the same in a laboratory channel. And once again, if you look at just at this, you can think of it as an alternate bar pattern. Then you just mirror it over the width of the channel, and you see this more complex pattern that has exactly the same kind of periodicity. This is a braiding. This is a braiding. So it's a situation in which you have, so you are at low flow. So during high flow, you have the formation of that multiple row bar bed. Then the flow goes down, and what comes out is typically a braided system. So a connection of many channels in the plant. Okay, do you still have some time? Yes, still half an hour. Okay. Okay, this is, I brought this to you because it's an example of what you can do with the experiment. Okay, this is a typically regime diagram. It was made by Engelund and Hansen, 1966. There are many other, one by Simon, who was one of the guys there. So this is built up in the in the laboratory. Okay, you perform many experiments. You choose two parameters. For example, here you have the fruit number, which is proportional to the sheath number, so to the average bed shear stress exerted by the flow over the bed. Here you have this ratio U over U star. You will learn to call it a non-dimensional chassis coefficient. So it's a conductance coefficient. In a sense, it's something that is related to the roughness of the bed in a very short way, in a very rough way. So it's something that has typically this value and describe you the relationship between the bed shear stress and the flow velocity. Okay, so for example, value of 20, typically it varies between 7 and 25. Value of 20 means a very fine material on the bed and a very shallow flow. So the ratio of the grain size over the flow depth is small. Let's say a small value of the ratio of the grain size over the flow depth gives you value of this coefficient of more than 20. If you go to shallower flow or to coarser material, this ratio increases, and then this conductance coefficient, Chassis coefficient, goes down, okay, and goes to 10. So here you have rough, coarser material and shallow flow. There you have finer material and flow depth. Of course, it is relative. Okay, you can have gravel with very big flow depth, or a shallow flow with very fine material still have a big, a small ratio of the two. So you can think in both ways, but the important thing is that they just do experiment for these different value of these two parameters, which characterize, in a sense, the resistance and then the bed shear stress, so the action of the flow on the sediment. And then the Froude number, so a parameter which is typical of the flow. Then you see if you go up with the Froude number, if you exceed 1, you are in the realm of anti-dunes. Actually, you start to see them at about 0.8 here, and then you go up to 1.5, 20. Forget for a moment about this plate back here. Stay around 20 or around 15. Okay, make a line on that. So if you lower the Froude number or you lower the shield stress, you have the formation of dunes here, and then I'm missing. Okay, these are all dunes. Okay, you have there a region in which between anti-dunes and dunes in which you have the formation, in which you have a plain bed solution. This is what is called the upper regime plain bed, upper plain bed regime. This one, which is something in between the formation of dunes and anti-dunes. So when you increase the Froude number, you will start to see the formation of dune, and then at some moment they will disappear, and you will have a plain bed solution. So the uniform flow, in a sense, is stable. Okay. After a stable uniform flow, then you will, if you increase the Froude number further, you will have the formation of anti-dunes and upper migrating backwards. Okay, please.
This is only for sand.
This is.
It says that the diagram is only valid for sand.
Well, if you move down here,
Yeah, that's what's.
it starts to become. It can be gravel. Okay,
so
it really.
you can use this also.
Yeah, it really depends on the ratio between the grain size and the flow depth.
Which is the one.
Which is that one. Okay, so in a sense you can say that you have gravel. You can think of an ideal experiment in which you keep the flow depth constant. Then if you move down, you are going toward coarser materials, so you have gravel. But it really depends on the ratio of the two.
Okay, so if you say that the whole thing here is for sand, it's only the flow depth that's varying on the y-axis then. Like the opposite of what you just said, if you just keep the substrate size constant.
Okay, yes, it is, but you shouldn't say that sand has just one diameter. Okay, you have finer, yeah, okay. You have finer sand, so it will still change. And you have finer material, finer sand on that side, and coarser sand on the other. And then sometimes you will move to gravel, but this is just a matter of let's say, definition on what a threshold is. Okay. Because most of the the distinction between sand and gravel is something that is, very difficult to make. In the sense that, indeed, in the space of the parameter, you have a continuum. Okay, so it's something that once again, it's quite easy to be defined, because if you look at that, it looks like sand, it looks like gravel. Also because there is a kind of a gap in rivers around some diameters that are of the order of the millimeter, then suddenly that fraction is not present in most of the rivers, so it's not really a continuous. But it's an artificial distinction in the space of the parameters. Okay? In the space of the parameters are typically non-dimensional. It's something which we'll try to, I will introduce to that in a moment. When you study these things, you want to have parameters that do not depend they are not dimensional, they are numbers, okay, like the full numbers or whatever. And that makes the distinction between sand and gravel very artificial, because if the parameter that controls the whole thing is the ratio between the two, then there should be some characteristic depth that means that sometimes you are in sand and sometimes you are in gravel. Okay. But in a sense, this is the limit of the analysis. Okay, this is exactly what I want to bring you. So the story of the parameters. There are many dimensional. When you study any physical phenomena, there are many dimensional quantities involved. Dimensional. Every one of you know what dimensional means, or non-dimensional. It's a concept that is. How much I have to insist on this, because I have to insist a lot with the students at the second year in the bachelor, because I mean, dimensional and non-dimensional things are something that is, let's say, black magic. If the other one is magic, this is black magic. But it's something. Let's start from this. There is a famous theorem. So if I call it a theorem, sounds very important thing, which is called the pi theorem, or the Buckingham theorem. Let's say that if you have any relationship between quantities in a physical problem, then if you introduce non-dimensional quantities, so quantities that are just number, that have no dimension, then the number of variables by which your functional depends reduces. Okay, so it's something that is very helpful when you are studying a problem in, let's say, in a lab, for example, because, for example, think of a phenomenon in which all these parameters are important. Okay, if I want to relate one of these parameters to the other, for example, the longitudinal wavelength of bars or the bathrooms to all the other, and I plan to do it experimentally, then I should make a lot of experiments in which I try to find the functional of this of the wavelength as it depends from all the other, which means it's 3, 6, 9. Okay, 9 parameter. For building up this functional, then I have to change one parameter in a range and keep all the other constant. Then do the same for the second one, the third one, and so and so and so. Of course, there are some of them that I cannot change. Gravity, for example. Oh, I can, but it's not so simple. Some parameters are already dimensionless. Think of the channel slope, for example. The slope is the ratio of length, so it's non-dimensional. But if I try to build up this functional, then this pi theorem or Buckingham theorem tells you that this functional of 9, the dependence on 9 variables can be reduced. And it typically can be reduced of 3 of them, which is not very much. And you can do better. But this is the idea which brings you from dimensional quantities to non-dimensional parameters. Okay, so in order to reduce the complexity or to reduce the dimension of the space of the parameter, then you introduce these non-dimensional parameters. And so you put in your cauldron, for example, the relative density, which is the ratio of the sediment density to the water density. And it's non-dimensional because it's a ratio of density. Then you have the sheaths parameter. I mentioned it before. It's a kind of non-dimensional bed shear stress. So you have the bed shear stress dimensional with a star. There are dimensional quantities divided by this group here. S is the relative density. Rho is the flow density. The fluid density. G is the gravitational acceleration, and d star is the diameter of the grain diameter. If you combine them like this, you obtain a non-dimensional shear stress, which is known as the sheaths parameter, and is quite used to determine, for example, the sediment discharge and all the quantity related to the sediment transport. Then you have the Freud number. The Freud number is something that characterizes the flow and is the ratio between these quantities. So it's the average velocity, u, depth average velocity over the square root of g and the flow depth at d star. Okay, this is the Freud number. Once again, dimensionally, the numerator of this fraction has the same dimension of the denominator, so they have, this is a number, it has no dimension. And the Freud number it characterizes the threshold between subcritical and supercritical flow. So, for example, a value of Freud equal 1 marks the boundary between the anti-dune regime and the dune regime. Okay, this is the Chessy coefficient, the one that I told you is the ratio of the average velocity over the friction velocity. Okay, let's forget about what the friction velocity is, but it's a ratio of two velocities, so it's non-dimensional. And it has been related to this, to the roughness of the bed and to the flow depth in this way. So this is exactly what I was telling you. This is the ratio of u over uf. So if you go to shallower flow, so if you decrease d or you increase the roughness and so the grain diameter. So if you decrease this or increase this, you decrease it, so C decreases. Okay, so lower value of this non-dimensional conductance coefficient means either shallower flow or coarser sediment. Higher values, about 20, of this conductance coefficient means the contrary of shallow, deep flow and fine material. Okay. Sometimes my English stops by its own. I cannot do anything. Okay. Okay, this is a part of the other one, so it's the ratio between the grain size, to depth ratio. So usually in with the same value of this ratio, you can handle, you can increase both of them and have the same ratio. So we can have deeper flow and coarser sediment be treated the same way, or of shallower and finer material. roughness is, okay, I already mentioned this, is the ratio of the roughness of the bed, which is proportional to the grain size and the flow depth. Okay, this is a weight number, so this is important because it's something that we will use a lot. The weight number is a kind of an inverse of the wavelength. So Lx is the wavelength. If you build up the number which is 2 pi d, or let's say 2 pi over L over d, so it's the ratio between it's the inverse of the ratio of L over d, so the ratio between the wavelength and the flow depth, multiplied by 2 pi. Okay, this is a convention. It is just what is called the wave number. Pay attention that smaller wave number are longer wavelength and vice versa. Okay, so you have shorter wavelength means larger wave numbers. Okay. That's it. Now we have reduced the number of parameters to these, which are the shear parameter, the fruit number, the Chassis coefficient, the non-dimensional grain size, and the non-dimensional bed roughness. We can do more because we can assume, as we usually do, that the bed roughness is related to the grain size of the bed. For example, this is a typical, so it's of the order of the flow depth with a proportionality constant that is about 2.5. Okay, so the roughness is a little larger than, because I remember you that the roughness measure the effect of the let's say the bed on the flow. Okay, so it shouldn't exactly be the roughness be equal to the diameter, but it's the effect of the presence of grains on the flow. If you introduce this, then of course you can you eliminate one of the two, and you can choose to describe your system. So when I told you about the state of the system, then the state of the morphodynamic system can be defined in terms of just two parameters, non-dimensional. You can choose either a dynamical, in a sense, parameter, which is either the Shields number or the fruit number. Okay, so you can have your parameter space with a Shields flavor, as I call it, or a fruit flavor. So in terms of the fruit number or in terms of the Shield number, because the two are related by this relationship. And the same is true for the Chassis non-dimensional coefficient and the non-dimensional roughness. Okay, so you can use either C or D to measure the roughness. The diagram that was made by Angel and Hansen has C on one axis, was U over UF, and fruit in the other. Okay, so you can use either one of the two and one of these two to set the state of your system in the space of the parameter. Okay? Any question on this? We're almost finished. What I want to show now is how you use the experiment. In particular, how you can use the experiment to find some characteristic scale of the problem. There is let's say a process in the identification of bedphones and patterns in general, which is related to the scaling, the characteristic scalings of these of each bedphones. In particular, for example, this shows you, this is the set, the data set of Guy, Simon, Sir Richardson I showed at the very beginning. Every point in this plot represents a run, and it's a black triangle if they found ripples. It's a blue square if they found anti-dunes at the end of the experiment. Red dots are dunes, and red triangles are something in between ripples and dunes. It's not always so easy to, even for the experimenter, to understand if you are looking at one species to the other. And so this graph has this main how can I say, meaning. So on the vertical axis you have the wavelength of the bedphones as measured by the experimenter, scaled with either the diameter, let's say the grain size in the above plot, and in the bottom plot the same quantity is scaled with the flow depth. Okay? And I want you to appreciate this, which is something that is very old actually. And so that anti-dunes and dunes scale much better with the flow depth than with the sediment diameter. Okay, you can see that the same markers collapse almost quite good, even if it's a logarithmic plot. But there is a clear tendency to a value of the ratio which is of the order 8, which means a wave number of order almost 1. Okay, because this is, if you have to do 2 pi over 8, 2 pi over 8 is a little less than 1. On the contrary, ripples scale much better with the diameter, even if the constant of proportionality is much larger, it's about 10,000 instead of 8, which means that it's not correct to say that is an order of magnitude, so that the wavelength is the same order of magnitude of the grain size. This is not true. But it's true that they relate much better to the grain size than to the flow depth. In the top, this relation of L over D about 1000 is a famous rule of the thumb for the estimating the ripple length given by Yalin, which did many experiments on ripple formation. Okay, so this is important because it gives you also information on the physics of the problem. So in a sense, you should expect that the wavelength of ripples, I told you before that ripples and dunes are quite similar from the point of view of the linear stability analysis, but this analysis tells you that you should expect the wavelength of ripples to be related to the grain size much more than to the depth. And on the contrary, dunes, the wavelength of dunes should be related with the flow depth much more than with the grain size. Okay? Both of the things have an influence, of course. So there is a different, so a cloud of points. But you see that when you catch the right scaling for the wavelength, then all the data tends to collapse on an arc. Okay, this is about 100 or so experiments, so it's pretty stable. And also there is a range in what you have here that is another parameter that you can build up, like a Reynolds number, build up with the grain diameters. This is the particle Reynolds number, so-called. But you can see that in a range of this, essentially, this means coarser material and finer material. Okay, good at that. In a relatively wide range, then you can see the scaling to apply much better. The same thing you can do that we have done with ripples and dunes, we can do with alternate bars and diagonal bars. If you look at this, you should say that the two things are exactly the same. Okay, it's a diagonal pattern, alternate, so very similar one to the other. The only thing is that this is much shorter than the other, but I mean it can depend on the parameter that we have chosen. Indeed, these are two very different kind of bed form. This one are the bar that I mentioned you before. This one is a diagonal dune, actually. So it's what happens. So dune are not necessarily unidimensional, monodimensional, but can also have an oblique front. Okay, and this, which have been called diagonal bars, add in confusion to confusion in the sense that they are not bars, but a dune are actually the oblique mode of a dune, which is different from the oblique for the transfer mode of alternate bars. So how can you realize this? You have to do exactly the same game that we did with ripple set unit. This is again, I have integrated the data set with also the run for the alternate bars and for these diagonal bars that I called. So the triangle, the black triangle is an alternate bar. The red triangle is this diagonal bar. And if you look at in the space of the parameters, so this time I have C, the conductance coefficient on the X, and you can see two things. First of all, that let's do this. First of all, that of course, when you scale the longitudinal wavelength with the flow depth, you obtain the same as before. So dunes and alpine dunes tend to scale well with the flow depth. Alternate bars are not scaling well with the flow depth. They group together when instead of using the flow depth, you use the width of the channel. Okay, so this is the typical. Guido will work a lot on this concept. The longitudinal wavelength of alternate bars scales with the width of the channel, not with the flow depth. So they have a different scaling, and in fact, you can see that if you plot the same data one time against the half of the width, so WH is half of the width, but it's just the same. If you scale the same quantity, so the same longitudinal wavelength with the width of the channel in the upper plot and the depth of the channel in the lower plot, then dune aggregate well with the scaling of the depth, and that on the scaling of the width, and the opposite is true for the alternate bars. And the interesting thing is that diagonal parts are just in the middle of the two. Okay, so in both cases they do not scale very well, neither with the width of the channel nor with the flow depth, because indeed they have they have both the scaling together. So they are duals, so they tend to scale with the flow depth, but they are also an oblique platform, so the width of the channel play a role, and they just fit in the between. Okay. Ok. 5 e mezza va bene? Se finiamo o è troppo tardi? Resistete ancora 20 minuti? Will you resist for 20 minutes more? Okay. The last thing is very easy. So it's has to do with this kind of thing. So I want to yeah, it's a bridge. Sorry. Not very stable actually, but it's an unstable bridge. It's a key to play a little game with you and to introduce two concepts that are important in the linear stability analysis of platforms. One is the free and forced instabilities, and the concept of resonance, which is connected to that. Okay, let's start from this concept of resonance. Resonance is a concept that most of you have studied in physics. Is when you give a little disturbance to a system and the system explodes. Okay, you hit some kind of you have a periodic forcing of your system, and you hit some characteristic frequency of that system, so that it starts to resonate and it explodes. This one is a very nice movie that you probably have seen many times, which is a famous collapse of the bridge, the Tacoma Bridge in the 40s. This is real. It looks incredibly sinusoidal actually, but I mean, is what's happened at the end. It can't resist anymore, and it collapsed. Okay, this is, I'm not sure was the engineer that that did the project.
No, he was the owner of car.
If you haven't seen it before, I mean, it's worth a couple of minutes. It's amazing. Okay, so and this happened for the wind. Okay.
The handbrake is working in that car.
At the end, I mean, it cannot resist anymore to this kind of stress, and then it collapses. Okay, I give you another example of a bridge.
A lot of sediments in the river.
Che cosa?
A lot of sediments in the river after the bridge.
Okay. This is much. Okay, this is it's real actually. Can you see it now? Can you see the oscillation? Look at the people and the structure. This was the first day of the bridge. It's scary. Look at the people. Same bridge. Have you seen the movie?
Harry Potter.
Good. This is magic, actually. It's so similar to the other one that I want to put it one together with the other. Okay. Question is, which one is a resonance?
Tacoma.
Okay. Who vote for Tacoma? Raise, come on.
Tacoma.
Okay. Who vote for Millennium? No one. Both are resonance. Okay. Who vote for both?
No.
Okay, let's do better. Okay. How many for Tacoma? People is convinced. Okay. 10. Millennium. Sooner? Both?
How is it possible?
This is impossible, but 6. Okay. Otherwise, I should have done the question. But okay. The answer? You know what is the answer. Come on.
20 minutes.
Okay.
Oh my god.
Okay. Okay. This is, I mean, it's a very common misconception, this one. Point is that resonance requires an external periodic forcing. Okay? So that resonates because there are people which is walking on the bridge and the frequency of the forcing walking on the bridge resonate with some natural frequency of the bridge, and this is the reason. Okay, so if people is walking with the same frequency of the system, this is the reason of the vibration, and luckily there was no collapse of the bridge. This is a paper of Nature in 2005, which says, okay, footbridges start to sway when packed with pedestrians falling into step with their vibrations. So they synchronize, and this is something that happens also because if you are walking on a bridge and the bridge starts to oscillate, then you tend to move your feet in time with the forcing, and so you force exactly that frequency, and so it tends to amplify and to resonate. And this is the reason why soldiers have to break step when they are crossing the bridge. Okay, so they are specifically requested. You see this is on Albert Bridge in London. That says all troops must break step when marching over this bridge, because if the people all together goes marching on the bridge, there is a risk that they force a natural frequency of that one, and so you can have this kind of resonance. Tacoma was not. So what was Tacoma? It could be in a resonance if, for example, you have kind of, you know what vortex shedding is. If you have a cylinder, you can see a sketch of it on the top. A flow which is investing a pole. It creates this kind of wake, oscillating wake, which could be possibly be the external forcing, because wind is going this direction, which can possibly produce the external forcing, making the bridge resonate. But actually, vortex shedding has a precise frequency. Okay, once you set the dimension of the flow and the intensity of the wind, then the shedding, the frequency of the vortex shedding is fixed, and this doesn't match with the frequency of oscillation, which is much faster than this one. So what it is, and this is just to mention the fact that it's not easy to understand, so you are not so wrong with that, because there is this paper, Resonant Tacoma Bridge Failure and Undergraduate Physics Textbook, and that which wants to, because in many physics undergraduate textbooks, that one is used as an example of the resonance. Actually, so it was not, it was a free instability, which is called flutter instability. And it is the one that you have with a flag, for example. Okay? You know that you have a wind that invests a flag, and the flag starts flapping like this. There is no external forcing, because forcing means that you have something which has a periodic behavior. Fluttering is just the result of the instability. Okay? And it's just because, there are differences in the pressure from one side or the other of the flag, and the flag flaps like this. How do you call the aliante in English? You are my expert in English. I'm lost without you. Okay, the no engine plane. Okay, and you can see that it's just the interaction between the structure and the wind, the elasticity of the structure and the wind. But this is a wind. This is a free instability. So there is no forcing. It's just that the interaction of the wing with changes the flow, and there is a feedback between the flow and the structure that makes the wing oscillates exactly like in bed forms. Okay. So the important thing, this is useful to distinguish between forced and free instability. When you consider the wind plus body system, so you consider the whole system, the plane with its wings, its elastic wings, and the air around it, then this is a free instability. So there is no forcing from the outside to the system, and it's exactly like bed form R. Okay, so if you consider the system composed by the flow and by the shape of the container, by the container, let's say, if you consider the system composed by the two of them, this is a free system. So it's subject to instability, and bed forms are the result of instability. As opposite, a forced instability in bed forms is what you have in meandering. So you can have bed forms which are forced by the curvature of the channel. Okay, so you can have free bed forms inside the meandering channel, but you also have a solution of the problem of a form of the bed, a pattern, which is related to an external forcing, which is the curvature of the channel. Okay. So if you study a steady channel, a steady meandering channel, one in which the banks are not changing in time, then this is an example of a forced solution. Because just the fact that you have some shape the river is meandering, this creates bed forms on the inside, on the outside of the bands. Okay? And these are forced bed forms, because are induced by the curvature, which is fixed. Okay? If you once again put together the sediment transport model, the flow in a meander, and you introduce some relationship between the flow and the bank so that the meander can evolve, that one is again a free system. Okay? And it cannot resonate, because the system composed by the bed, the flow, and an erodible bank, it will evolve, it will have its own instability, it will produce meandering, and increasing meandering and so on, but there is no forcing from the outside anymore. The only way to have a resonance is when you have a forcing. Okay, this was the concept, and we will go back in both these examples. So the distinction between point bars and free bars, the alternate bars I show you are free bars, is built upon this concept of the resonance. So if you study the solution in a meanders, then you will have a forced solution, and sometimes, if we don't have time to show it to you, it will talk you about some resonant value of the width adaptation. Okay, which is exactly that. So it will be the situation in which the forcing associated to the curvature influence the dynamics of free bar in the channel. Okay, we will also talk about tomorrow about resonance, which is, however, an unphysical resonance. So it's related to some simplification that you can do on the system, which we'll discuss, which introduce this forcing. Because, okay, I will tell you tomorrow, because so I will not spoil the solution. Okay, that's it for today. Thank you for your patience.